steps. It's not simultaneous. It can pick up 2 electrons, it can pick up protons, but it's mainly an electron shuttle. It's not a proton pumper. Cytochrome C has a similar function, but a much more complicated shape. It requires heme, which requires iron. So some of the iron that your body needs is not just to make hemoglobin, but it's to make cytochrome C to carry electrons for you. Cytochrome C is specifically on the outer surface of the inner mitochondrial membrane. So if I go back to this picture, they've been very intentional about where they draw ubiquinone and where they draw cytochrome C. So ubiquinone, in essence, is buried within the inner mitochondrial membrane. Cytochrome C is kind of floating along the outer leaflet here. So again, that's important because in a real mitochondrion or a real cell, these are not arranged in rows. They're just, everything is floating place to place. So you could have a cytochrome C over here, you could have a ubiquinone here. These complex 1, 3, 4 are not in lines. They're drifting all in the inner mitochondrial membrane. So you might think, well, how can they know who to pass electrons to? This is how. The reason that the electron transport chain works in the order that it does, it is not specifically about the spatial lineup of the proteins. It's about their redox potential. So this is showing, what's the free energy per electron, what's the redox potential of that component, and it's showing that NADH dehydrogenase, for example, can only receive electrons at that particular reduction potential. I'm just going to say that again, exactly the same. NADH dehydrogenase complex can only receive electrons at this level of redox potential, which in this system, only NADH has electrons like that to give. Here's another example. Cytochrome C can only receive electrons at this level of redox potential, and in this system, the chemical that has electrons with that redox potential is cytochrome BC1 complex. So that's why cytochrome BC1 complex is able to donate electrons to cytochrome C, and that's why cytochrome C preferentially reduces cytochrome oxidase complex. It's because the redox potentials are, let's say, they're falling throughout this chain. This is a really important chemical concept. And the reason why oxygen has to be the one that takes electrons from cytochrome oxidase is that oxygen is the only molecule around that can accept electrons with that crummy of a reduction potential. So as you look at this, the electrons are losing energy. They're losing their own energy as they go through this chain, and they will be preferentially accepted by the molecule that accepts that redox potential of electron. So that's why electrons move the way that they do through this set of cell machinery. That's why they go the direction that they do. So if you imagine all of this as a sea, an ocean of intermixed redox partners, that's how the cell keeps it straight where the electrons are supposed to go. It doesn't have to be lined up in a line. It's just, oh, am I close to my redox partner? Here you go, here's some electrons. That's That's the rationale behind how that works. This slide is using our book's kind of graphical representation of there's energy input that drives a paired process. So ask yourself, what is the energy input that is driving these types of proteins to form new energy requiring configurations? What's the energy that's powering the shape shifts in these enzymes? It's on the slide. I didn't notice that until after I asked the question. It's the energy from electrons picked up by these pumping proteins. So NADH dehydrogenase, cytochrome BC1 oxidase, cytochrome oxidase. That lets them, they picked up a proton, and then the energy from electrons are pushing a new configuration. And that proton happens to get pushed out the other side. So as you look at this, you might think, well, okay, the proton is joining, and then there was a shift, and then the proton got released. The timing of where the electrons are joining and leaving with this, I don't want to get into here. But don't worry about that too much for this class, but it's the electron energy that is pushing configurational state changes that lets a proton leave on the intermembrane space side. And then for the last slide that I want to go over is the concept of what is an uncoupling agent. An uncoupling agent. So there are certain poisons or toxins that are particularly deadly to people or to animals that use these kind of electron transport chains. And what they do is they insert into membranes and they create an alternative pathway for protons to go through the inner mitochondrial membrane. And the more that you have of them, the more protons will go down their gradient without spinning, can't do it with my left hand, without spinning ATP synthase. So these are acting to uncouple proton gradient from ATP generation. That's what an uncoupling agent is, and they are particularly harmful to people. So that's where I'm going to stop this little half lecture. I hope it made sense. If you have questions about things that I said, definitely talk to me before the exam. But you definitely want to know your electron transport chain components, what's their order supposed to be, what are their complex names, and how are electrons and protons generally moving through this system. Okay? We'll see you soon.